Hey everybody, this is your friendly neighborhood statistics professor letting you know about your midterm examination coming up this week, as if you didn't already know. But in preparation for that examination, we're going to have a little fun right now reviewing some of the stuff we have covered and talking a bit about the format of the exam. So, if you don't remember, or maybe you didn't realize it because you've been out of touch with the world, your midterm exam is this coming Tuesday, Halloween, October 31st. And my friends, it's online. That's right. It's 2017, I think. I'm pretty sure. So we're doing stuff online now. So we're going to talk about what we've learned up to this point, and we're going to describe the midterm for you because you all are freaking out and you are the generation of anxiety. So I'm here to help quell your anxiety, my friends. Now, the only formula that I'm going to give you on the exam, I'm pretty sure that's on the exam, I haven't really checked in a bit, are these. This is the formula for the one sample t-test, and this is the formula for the dependent samples t-test. Right now, because this is an online exam, it's also open book. You can look at whatever you want. You could even Google some shit. I don't recommend it because you haven't got a lot of time to answer each question. So you should have things in front of you for easy consultation. I'm not giving you any Z tables or T tables, so you can look up anything you need at the back of the book, as you have been doing for your homework assignments. And even if I have given you these formulas, you may still want to write them down for yourself in a fashion that is convenient and accessible for you. Right. That's what I'm giving you. So it's open book and you can access whatever you want. But again, the time is short, so have things arrayed in an efficient, useful way. So what's on the exam? The exam consists of 70 questions divided across 8 separate independent quizzes. That means, my friends, that you can do one quiz, take a break, call your mother, get some, calm down a bit, have a drink, then go back and do the next quiz. Because you've got from 5 p.m. till midnight to do all 8 quizzes. That's how generous I am. 5 p.m. till midnight. The quizzes will become available starting at 5 p.m. on Tuesday, and they will stop being available at 11:59 p.m. Tuesday night. So you can choose to allocate your time however you wish. What I recommend is you do the first one, see how difficult or easy it is. If it's too difficult, then go back and study some more, then continue on and do the remaining quizzes. The total time allocated for all 8 quizzes is 100 minutes. But you can spread those 100 minutes across 7 hours. So I fully expect everyone to get near perfect on this exam. Okay, so that's how generous I am. Now, as I mentioned, there are 70 questions total, all of which are multiple choice. Multiple choice. And of those 70, you could use math on 5 of them, but you don't really need to, right? The answers are fairly obvious. And 5 of them you actually do need to use actual math on. And of those 5 questions, you've got 2 probability questions, 2 bivariate analyses. Remember, bivariate analyses are things like odds ratios and relative risks, and 1 t-test. Straightforward, no nonsense. The rest are theory-based, and we'll give you some examples of what theory looks like. What will not be on the test? Well, I will not ask you to calculate anything involving z-scores, because really, nobody does. I will definitely not ask you to calculate anything involving correlation coefficients on this exam. I know one of the homework questions asked for that because I want you to experience it, but on this exam, why bother? It's just grunt work. And lastly, I will not ask you to do any calculations involving the independent samples t-test, just possibly the one sample or the dependent samples t-test. So, where you get your exam? Well, when you log on to Brightspace, on your left-hand menu, you will see all these things from the course, and you'll see this chunk called the midterm exam. Under the midterm exam module, there are practice questions. I'm sure you've seen those already. There's a sample quiz. We'll talk about that in a second. And the actual exam. The actual exam will become visible to you on October 31st at 5 p.m. But you click on that, and these links will pop up. There are actually 8 of them. I'm only showing 5 here. Notice it says here in each one, starts October 31st, 5 p.m., and ends at 11:59 p.m. So you've got all that time to access each of these. 8 of them total, right? So the reason I've separated them out in chunks is A, to give you a break in between in case you freak out, because I know, you young'uns have a penchant for freaking out. And the second reason is just in case there is a technical failure, the entire exam won't be lost, just independent chunks, right? I don't expect any technical failures, but if one does pop up, I can more easily address a single chunk being lost than the entire exam. That's how smart I am. I plan for these things. Now, there is an introduction at the front of the midterm exam module, and it says this. It explains what's going to happen. Each of these eight quizzes is time limited. Down here I've shown you how many questions are in each quiz and how many minutes you have total. Those of you who have accommodations with SAS, you have already been given extensions associated with your accommodations. So don't worry about that. It's built into the system. I hope I've done that correctly. If not, then you got the same time here. Okay, so this is an open book test, but it's your responsibility to know the material accordingly. That means I don't recommend you start looking shit up. I recommend you array your notes and stuff in front of you. Now, each quiz, not all of them, but most of them, have random questions. And because multiple choice, the actual choices are also random. Why? That's because you're supposed to do this independently and not collaborate with your friends. But I know someone's going to try to cheat. I know. It happens all the time. So if you're sitting next to somebody and say, what'd you get from question 6? It won't be the same question 6, and item B will not be the same item B, and item C will not be the same item C. And because you've only got a short time to do this, there ain't a whole lot of time to collaborate, so do not try. And if I find out you did, well, something nasty is going to hit a spinning thing that you use to keep yourself cool. The shit's going to hit the fan. That's what I'm trying to say. So, you're expected to do this by yourself without collaboration. You can do it anywhere you want. You can do it at home, you can do it on campus, you can do it at Bridgehead or Starbucks, doesn't matter. However, I advise you to do so at a place where the Wi-Fi is reliable. So if you're really, really scared about that, do it on campus, because then at least the university is responsible for the Wi-Fi, and I'll have evidence in case the Wi-Fi has failed. So if you do have a technical failure of any kind, photograph it. So just give me some kind of evidence to show that it actually happened. And I mentioned there are a total of 70 questions. You have 100 minutes total to do them all. But you can do them all in one sitting, or you can do one, take a break, do another one, take a break, right? But you've got to get them all done by midnight. If it's not done by midnight, it does not get marked. This is not an assignment, it's an exam. Okay, as well I mentioned there is a sample quiz, and the sample quiz is there just for you to get a sense of how the technology works. I advise you to try it out right away to make sure your device is compatible, to make sure you've got all the flash download stuff, and if you're using a tablet, it works on your tablet, etc., etc. So if you click on sample quiz, this thing pops up. This is how your test will look. So the question, press at your hand, is A, good looking, B, but ugly, C, however, obviously it's, which one is it? Oh, it's C. It's clearly C. Oh, wow. Look at that. C and D are the same. Interesting. Interesting. Wow, both of those are correct then. So as you can see on the left-hand side, on each page it shows you how many questions are available. So the way that these quizzes are set up, each quiz you will have all the questions visible to you at once. So you can choose which ones to do first. But then once you've submitted them, you cannot go back and edit. Right? And you'll see that in this example. Right, so that's the exam. Now let's go over what we have learned thus far in class, therefore, what is testable on the midterm exam. What have we learned? Dun, 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 dun. Well, in the first lecture, and by the way, when I say a lecture, I mean like there are 2 lectures per class. So, lecture 1, lecture 2 happen on the same night. So lecture 1, we learned about the differences between continuous and categorical variables. I think you're all clear on what that is. We learned about the levels of measurement, and hint, hint, this is fairly important, so I would like you to spend some time really understanding this. There's the nominal, ordinal, interval, and ratio measurement. So nominals are names, categories, things you can't rank. Ordinals are rankings. Interval and ratio are continuous variables, and the distinction between these two is that this has a rational zero and interval does not. This table summarizes well the kinds of math you can do on the various levels of measurement. We mentioned sampling and how this works in research. So we are always selecting a sample to perform statistics on to learn about the reference population. So if I'm trying to figure out the average weight of second-year stats students, I take a sample of second-year stats students, I compute the average weight, and I do some kind of magical mathematics to infer the average weight of all second-year stats students. So that brings us to the distinction between descriptive statistics and inferential statistics. As I mentioned, descriptive statistics is how I describe, hence the word describe, the sample. And the sample is the people I have in front of me, the data that I have in front of me, the thing that I've collected. So the average age of women in this class, that's a description of my sample. Inferential statistics is when I attempt to make conclusions from the sample about the reference. I infer something about the reference. And most of frequentist statistics is about inferential statistics. That brings us to the terminology that distinguishes between parameters and statistics. A statistic is what we have in our sample, a number from our sample. A parameter is that same descriptor, but for the reference population. And most typically, we actually don't have a parameter. This is usually a theoretical construct, but sometimes it isn't. Example, the average daily calories consumed by all children in Toronto. That's a parameter, because I can't collect that. It's not possible. That's what I want to learn about. But my sample of 300 kids in one particular school district, that's my statistics. And I will use my mathematical techniques to estimate the parameter from the statistic. Lecture 2, we talked about research questions, right? And we mentioned that there are variables in research questions, and these variables are the independent variable and the dependent variable. The independent variable is the thing that you are free to be. The dependent variable is the thing that depends on the independent variable. So in this example, in hospitalized children, does music reduce stress? So you're free to listen to the music, it's independent, yes or no, but whether or not stress is reduced from listening to that music, well, that's depending on the music. And that's the question we are trying to answer in our study. Another example, smoking, you are free to smoke if you want to, so that's the independent variable, but whether or not you develop cancer depends on whether or not you smoked. So that's the dependent variable. We mentioned as well how to define a variable, and that it has two phases, the conceptual phase and the operational phase. So a variable is like a bucket, and data goes into that bucket. But the bucket is not the thing that you're measuring. The data is the thing you're measuring. The variable is just how you describe it. And that's not really that important in real life. It's just conceptually, intellectually important to draw that distinction. The example I like to give is, if I'm trying to measure how happy you are, I may ask you on a scale of 1 to 5, how happy are you? And you say 4. What does that mean? Well, that's the bucket that I've created for measuring happiness. But 4 is not happiness. 4 is a measurement of happiness. And 4, that bucket, has some limitations of what I can do with it. It doesn't tell the full, comprehensive, holistic story of happiness. Same thing. I just repeated myself. Okay, then we went on to frequency distributions, which really gets into the heart of inferential statistics. So frequency distribution is how we arrange the values in our sample. We count how many times each value occurs. So how many 25-year-olds do I have, how many 24-year-olds, how many 23-year-olds, etc. And I can display this in a variety of ways, most typically a table or a graph. So what I do is I count them all up, and I can compute relative frequencies, absolute frequencies, cumulative frequencies. Here's an example of a table showing my frequencies. Or more commonly, I show it as a graph. So histograms, bar graphs, pie charts, and these things called frequency polygons. This is a frequency polygon. It looks like a histogram, but things are pointy rather than flat. That's really the real difference. So when we talked about distributions, we said there are three ways to describe a distribution in terms of its modality, its symmetry, and its kurtosis. So modality is how many peaks it has. And you will recall that I gave you a fairly pornographic description of this image here, which I will not repeat because other people are watching this on YouTube now. But unimodal simply means one peak, bimodal 2 peaks, trimodal 3 peaks, and so forth. That's the mode. Symmetry tells us how far from the center, the of centrality the distribution is, so how skewed it is. Now a positive skew is when the tail strays off to the right. So it looks like this. Positive skew looks like that. Oh, right there. And negative skew is when it trails off to the left. To me, that's counterintuitive, but that's how it works, right? Positive goes this way, negative goes that way. Kurtosis is the flatness of it, and there are three possible types of kurtosis: leptokurtic, platykurtic, and mesokurtic. So leptokurtic is very thin, platykurtic very flat, like a platypus, and mesokurtic is somewhere in between. Okay, so both skewness and kurtosis have a index associated with it. So with kurtosis, the positive values have greater peakedness, more towards lepto, and the negative ones have less peakedness, more towards platy. And remember, the skewness had a index as well. So here's an example of a leptokurtic with a positive index and a platykurtic with a negative index. So then we talked about measurements of central tendency. If you recall, central tendency is how do we describe the typicalness of our sample? Is the typical age of students in my class, is that given by the mean age, the median age, or the mode age? Right? We also looked at indices of variability. So how wide is my sample? How atypical are various elements in my sample? And we said that we can do so in at least 4 ways. The range, the highest number minus the lowest number. The interquartile range, Q1, Q2, the difference between Q2 and Q3. Standard deviation we looked at, and variance, which is the square of standard deviation. And we use the interquartile range to define our outliers, both mild and extreme. So a mild outlier, we define it this way: a score that is between 1.5 to 3 times the value of the IQR, and extreme if it's greater than 3 times the value of the IQR. So standard deviation, we said, is the average deviation score, or the typical deviation score. And deviation is the difference between e-score and the average. So this is your deviation. This is an individual score in your sample. This is the mean. A deviation is just that minus that. So if your scale is nominal, then the best way to measure typicalness is the mode. If your scale is ordinal, the best way is the median, and we can use the IQR, or the range, to describe variability. And for the good numbers, the continuous numbers, the best thing to use is the mean, and we can do all kinds of math once we have the mean. So in lecture 4, we went more into standard deviation. So we looked at the standard deviation equation, the square root of all the sums of deviations divided by n minus 1. And by the way, you'll see that in the sample we use n minus 1 as our denominator, and for the parameter we use n as the denominator. I won't get too upset if you mix that up. The options in the multiple choice exam are forgiving enough that it's fairly obvious which one you mean. So don't be too concerned if you get that a little screwed up. Variance is an important measurement of width as well, and the variance is a square of the standard deviation. And remember this notation. So we said the sigma is the parameter for standard deviation, whereas the lowercase s tends to be the statistic. At least in the textbook, sometimes we say SD. And sigma squared is variance, and s squared is the variance in the sample. Okay, so relative standing is a way of measuring how well or where in the scale a particular score sits relative to other things in the score. We use relative standing to compare things like how well you're doing in one class versus another class, or how well you did on the MCAT score versus everybody else. So we can do percentile ranks, or these things called standard scores or Z scores. So standard scores, Z statistics, Z values, or the normal score all mean the same thing. And it's a measurement of how far a particular thing in your sample is from the mean. So how far is your midterm mark away from the mean midterm mark? And we need to know the parameters of the population in order to have meaning for a Z score, the mean and the standard deviation. And this is the formula for a Z score. It's your score minus the mean of the distribution divided by the standard deviation of that distribution. And really, what the Z tells us is how many standard deviations away from the mean your mark is. So if you got 78% on the midterm, is that good or bad? Well, you don't know unless you know how everybody else did. So if the mean mark in class is 90, you didn't do that great, right? So how much less than the mean is your 78? If the mean mark was 50, then how much better than the mean was your 78? And we measure that in terms of the number of standard deviations. Now, if this is the distribution of all the marks, and your mark is over here, okay, you've got this score here, how many standard deviations from the mean is that? Well, we know that by looking it up in the back of the book. So we compute our Z score from the previous formula, look up in the back of the book to figure out what percentage, what probability this corresponds to. That's from the back of the book here. Okay, 1.64 is right there. So the 3 sigma rule tells us that within one standard deviation of the mean, you got about 68% of all the sample. Within 2 standard deviations, you get about 95%. And 3 standard deviations, you get 99%. Okay. Lecture 5, we ventured into the world of probability. That makes some people very uncomfortable. And probability just is if you can figure out all the possible outcomes of a thing you're looking at, and then look at what are you trying to detect, and just divide the two, and that's your probability. So what's the probability of getting a head on a single coin flip? Well, how many possibilities are there? Well, there's 2 possibilities, a head or a tail. That's 2. How many am I looking at? Well, just 1. So it's 1 out of 2. That's fairly obvious, right? So we did Boolean operators when we talked about probability, or, and not. That's pretty straightforward. And then we moved on to these measurements of bivariate association. Before we could do so, we had to do a review of study designs. Well, I guess it's not a review for you guys because you haven't done research methods yet. But we looked at cohort studies and case control studies. So a cohort study moves forward in time. That's when we ascertain the exposure status first and wait to see if an outcome manifests. So we ascertain who's smoking, who isn't smoking, and wait to see how many develop cancer. A case control is the opposite. We ascertain the outcome first, and we look backwards in time to see what the exposure was. So we find some people with cancer, some people without cancer, and we ask them, did you smoke? Did you smoke? And do the math that way. So cohort ascertains exposure first, case control ascertains outcome first. Cohort usually is moving forward in time, and case control is usually moving backwards in time. Example, is the taking of antiretroviral drugs associated with developing nausea? So this design, we find some nauseous and non-nauseous people, and we check to see if any of them took antiretroviral drugs. What kind of design is this? Well, nausea is the outcome, because we're saying that the retroviral drugs cause the nausea. If we are ascertaining the outcome first and looking backwards in time to see who took the drugs, that's a case control study. So based upon those study designs, we looked at contingency tables. In this case, a 2x2 contingency table. And to set up your table, it must always look like this, with the outcome vertically and the exposure status horizontally, and the outcome, positive outcome, meaning you got the thing, being first, and the positive exposure, meaning you're exposed to the thing first. Okay, so these are the numbers we care about. And then we looked at the various measurements of bivariate association that you can compute given that contingency table. We said there is the absolute risk reduction. Well, the absolute risk is going to be amongst those who got the exposure, what percentage got the outcome. So 75 out of 100, that's 75%. That's the absolute risk in this group. In this group, the absolute risk would be 10 out of 100, so 10%. So that's the absolute risk in those two groups. The absolute risk reduction is going to be the difference between the two. The relative risk is going to be the quotient of the two. The relative risk reduction is going to be this first one divided by the absolute risk in the second row. And the odds ratio is this fancy little equation over here. So the odds in the exposed group divided by the odds in the non-exposed group. Or the cross product divisor. I said that wrong. It doesn't make any sense. Cross product divisor. It just means multiply the A and the D and divide by the B and the C. That's how you do an odds ratio. So, correlation. A correlation is how we describe the relationship between two continuous variables. What we just saw over here, that's a relationship between two dichotomous categorical variables, like gender, male and female, and graduation status, undergrad versus grad student. Those are two dichotomous variables. We can compute an odds ratio between those two variables and figure out, are you more likely to be a grad student if you're female, for example. With a continuous variable, we're talking of things like age or height or income or weight. And we're looking at correlations between those. We can't do 2x2 tables for continuous variables, but we can compute a correlation. And if we do that, we can compute something called Spearman's rho or Spearman's R. This is our coefficient of correlation. And I said that this is this table we will be using to interpret Spearman's rho. The closer you get to 1, the better the correlation. The closer to 0, the worse correlation. And if I put a negative sign behind these, then it's just in the negative direction. So a -1 correlation is a perfect correlation just in the other direction. So this is a negative correlation. This is kind of a negative correlation. That's a positive correlation. And that's a nothing correlation. Nothing going on here. So, in Lecture 8, we talked about hypotheses, statistical research hypotheses. And we said there are two kinds, the null and the alternate or alternative. The null hypothesis always says nothing's going on, and that's the baseline state of things. We always assume that is the truth, and we're looking for the experiment, the study, the math, the science to give us sufficient reason to reject the null. We never accept the null. We can only reject it or fail to reject it philosophically. So the opposite of a null is the alternative hypothesis, or something's going on. We write it this way. The null hypothesis is H sub naught, H sub 0, and the alternate or alternative hypothesis is H sub A or H sub 1. So we talked about the types of error, type 1 and type 2 error. It's really important to get this straight because these two terms will come back a lot in your health sciences career. So I gave you the courtroom analogy where a man is on trial for murder. And let's say he's innocent, but you convict him anyway. You've performed a type 1 error. You've incorrectly rejected the null. The null says he's innocent. Nothing's going on, right? But if you reject that null and say that he's guilty, but he's actually innocent, you've committed a type 1 error. The type 2 error is when he's actually guilty, but you set him free. In other words, you accepted the null or you failed to reject it, but you should have rejected it. So get those things straight in your head. The difference between a type 1 error and a type 2 error. Now, then we talked about directionality in our statistical tests. We talked about one-tailed tests versus two-tailed tests. And the difference is very simple. They come up because if you think about this normal distribution again, we're looking to see if your sample is in the extreme or somewhere in the middle. If we don't care whether it's extreme to the left or extreme to the right, meaning we don't care if your midterm mark is really, really high or really, really low, we just care that it's not typical, that's a two-tailed test. If we do care, if we only care that it's really, really, really low, that's a one-tailed test. All right, so keep that straight in your mind, one-tailed test versus two-tailed test. Then we got into the more esoteric stuff, and this is where I tend to lose people. So we talked about the sampling distribution of the mean. This is a theoretical distribution of stuff. The example I gave you in class was if you imagine that we are testing IQs of 10-year-old kids in schools across Ottawa. Forget Ottawa, schools across the world, right? So we got like, X billions of kids around the world. And so I choose 25 kids from a class, I compute their IQ, I take the average, I write it down, I throw those kids back in their school, I take another 25 kids, I compute their mean IQ, write that down, throw them back. Another 25 kids, compute their mean IQ, write it down. And I do this a billion times until I got like a billion average IQs for my various sample size of 25. If I then look at how many times did I write down 100, right? How many times did I write down 98? How many times did I write down 5? Eventually, I have a plot of that frequency distribution, and it's a normal distribution. That is the sampling distribution of the mean. The mean what? The mean IQ I was computing from each of those freaking 25 samples. Okay, it's a theoretical distribution because I'm not going to pick 25 kids a billion times. I'm not going to do it. If I did, I'm pretty sure I'd find that distribution. The standard error of the mean, as opposed to the standard distribution of the mean, the standard error of the mean is the standard deviation of that thing I just made. Okay, so I just took all those kids and I wrote down their IQs. If I now compute the standard deviation of that sample, that is the SEM, the standard error of the mean. It's just the standard deviation of this theoretical construct. So how do I estimate this thing called the standard error of the mean? Well, because it's a theoretical thing, I can't get access to it. What I can get access to is one of those groups of 25 kids. Right? That's what I can get access. So if I grab one of those groups of 25 kids, I compute the standard deviation of that one group, and I divide it by the square root of how many kids there were. In this case, square root of 25, so 5. That will give me an estimate of the standard error of the mean for this theoretical thing. That's all that means. Now, I can compute a confidence interval. Remember what that is? A confidence interval is the estimate of the thing I care about plus or minus some error estimate. Okay? And this is given to me by, let's say I'm doing IQs again. I'm trying to figure out the probable average IQ of 10-year-old kids, and I've done all that work. I've got my 25 kids and I computed their IQ, and I just computed the SEM as well. So I've got the mean IQ of my sample plus or minus a t-value times the SEM I just computed, and that will give me the range of the confidence interval. Now where do I get this? I get this from the back of the book. Now, there's another theoretical thing we can look into, and that's called the standard error of the difference. So just now we looked at the standard error of the mean, but now we're going to look at the standard error of the difference. So in the previous example, I plucked out a billion random samples of 25 kids. Let's say instead of writing down their IQs, I subtract their average IQs from another billion random samples of 25 kids. So instead of writing down mean IQs, I'm writing down the differences in mean IQs. Right? That'll also give me a distribution like this. And the standard deviation of that new super curve isn't the SEM, it's this thing we call the SED. Guess what? It's the same nonsense. It's the same bloody nonsense. Instead of computing it, instead of actually measuring it, we can compute it with almost exactly the same formula. If that confuses you, forget about it. It ain't going to change your life. So then we moved on to the t-test. The t-test is a way of comparing means. And if you go on to do any kind of research in your life, chances are you'll do t-tests all the bloody time. There are two ways to do a t-test. One is when we compare the mean sample that we have, the mean value in a sample, to an external value. Like, is the mean mark of my class 85? Is the mean weight of 20-year-old women in Canada 125 pounds? Right? That's the easiest way of doing so. Or we can compare the mean values of two separate samples. Like, is the mean mark of two classes the same? So we looked at p-values then, and we said the p-value tells us whether or not to reject the null hypothesis. If we reject the null, we are saying that our observation is statistically significant. When do we reject the null? When the p-value is low. P is low, then null must go. When is it low? When it's less than or equal to alpha. What is alpha? If you don't know otherwise, it's 0.05. Why? Because that's what we decided. No other reason. Okay, so in other words, you compute a p-value to determine if it's low enough to allow you to reject the null hypothesis. If you reject the null hypothesis, you're saying something's going on and my finding is statistically significant. That's not the only way of doing things. I can do it this way, or I can compute a confidence interval. Both of those approaches give me the same result. So, t-tests are all about what? They're about comparing means, not medians or proportions. So, we can only perform t-tests on data from which we can actually compute means. Can we compute a mean from a set of names? What's the mean Shirley? What's the mean Bob? You can't do that. How about a list of rankings? What's the mean ranking of your favorite baseball team? You could do it. It doesn't have any meaning because rankings are ordinal data, and you can't compute means of ordinal data. It has no meaning. So you can only perform t-tests on data that is interval or ratio, because only interval or ratio data can you compute means for. When can you do a t-test? Well, as I mentioned, you can do a t-test when you're comparing two samples, like this class versus that class, this drug versus that drug, or when you're comparing the mean of one sample to a specific value, like is the mean IQ of 10-year-old kids 100. Okay, this is another way of looking at it. Let's say you're doing a test, a randomized controlled trial, comparing the mean number of headaches per year experienced by people who are taking this new fancy drug versus people who are not taking the mean fancy drug. Okay, so this is how many headaches are typically experienced in both groups. And there's going to be a difference here. The question is this difference great enough to say, oh, you know what? Something's going on here. If something's going on, we can reject the null. If it's small enough, we say, oh, you know what? We can't reject the null. Nothing's going on. This is why we perform the t-test, to determine whether or not we can reject the null hypothesis that says nothing's going on. These two are the same. So, as I keep trying to say in class, and maybe I'm not getting through to some people, what we're actually doing here philosophically is trying to figure out, is the mean that we have in our sample, is that close enough to this mean of a theoretical distribution that we can say, you know what, it's so close that it's essentially the same thing. It's essentially part of this magical universe where that's the mean. Or is it so different that I can't blind myself anymore? It is so different that this is not from this universe where things look like this. That's what statistical significance is. It's statistically significant. We say, my sample is so unlike the mean of this distribution that I got to throw out this distribution. It doesn't describe the world anymore. Right? And that's why we struggle with defining what the cutoff is for saying it's sufficiently far away or not. And we say that right now that cutoff is 0.05. If it's 5% here, then we say, oh, you know what, it's sufficiently weird that this is something special going on. Okay, I've lost you, I'm pretty sure, so let's move on. So remember, t-tests come in two types, the single sample or the two sample. The two samples come in two types, dependent, independent. The independent comes in two types, types in which the variance is the same or types in which the variance is different. Example, let's say we are comparing a mean to an external value. Okay, do we have an example of that? Average IQ. I've got 25 kids. I compute their IQ. Well, is it statistically the same as 100? An example of a situation requiring an independent samples t-test. Well, maybe again I'm comparing the average mark of the stats class in the morning to the average mark of a stats class at night. Two different sets of students, but doing similar work. Or in the dependent samples example, I'm comparing your midterm mark with your final mark because you guys being tested twice. Those are related. So, with the independent samples t-test, right, the ones in which we're testing two unrelated samples, so the morning stats class versus the evening stats class. Okay, so there are two types of these independent samples. What are the two types? Something to do with variance. So the variance is the same as the variance is different. How do I know which one to use? Some kind of test. Which test? This thing called Levene's F-test. So if we are going to use the independent samples t-test, we need to know if the variances of the two samples are different or the same, and Levene's F-test tells us that. Example, researcher wants to find out if plants grow faster with fertilizer 1 or fertilizer 2. So he starts with some seeds, he grows plants in identical conditions, same soil, same amount of light, same amount of water, he talks to them the same amount of time, he loves them and cuddles them the same amount. I don't know, I don't grow plants, I don't know what you do, right? But he uses brand 1 fertilizer to 7 plants and brand 2 fertilizer to 6 plants. What is the null hypothesis for this question? It's going to be that there is no difference between growth rate for brand 1 versus growth rate for brand 2. So the mean growth rate will be the same for both of them. In this case, it's height, so the mean height. So this is the SPSS output, and I will give you something like this on an exam. Here's some SPSS output, so compute it, interpret it rather. Right? So look at this output here. Here we have two rows. Equal variances assumed, equal variances not assumed. Which one do we look at? First of all, what do these columns mean? Well, this is the F-test. We start here. The F-test says the F value is that, and the significance, the p-value, is this. So, Levene's F-test has its own null hypothesis. Remember, the null hypothesis always says nothing's going on, everything's the same. What's the same? Variances are the same. Okay? So, if the null hypothesis for Levene's F-test is that variances are the same, look at the p-value here. Where's my cursor? Come back, cursor. Come back, cursor. There you are. Right? P-value is 0.79. Is that low or high? It's high because the cutoff is 0.05. This is much higher than 0.05. Right? So if the p is low, the null must go. Is the p low? The p is not low. The p is high. The null does not go. If the null does not go, that means we do not reject the null hypothesis. The null hypothesis said the variances are the same. We do not reject that. Therefore, the variances are the same. Which row tells us the variances are the same? The first one does. Equal variances are assumed. We read the first line until we get to the t-test. This all is for the t-test now. Right? So read across here. That's the t-value. That's the degrees of freedom. This is the p-value. Look at the p-value for this first row. 0.269. That is the p-value for this t-test. It's not 0.265. It's 0.269. Okay? Is that low or high? That's high as well. It's over 0.05. So we reject the null. Which null? Well, the t-test has its own null. Where's my cursor? Come back, your cursor. Remember, this is the main null now for the research question. The null we said was that the heights of the two plants are the same. Okay? Do we reject the null? We do not. Why? Because the p is not low. If we do not reject the null, we retain the null. The null says the heights are the same. Done! That's the answer to the question. Are the heights the same or different? They are the same. Okay. Again, what is the null hypothesis for Levene's f-test? That the variances are the same. So, are the mean growth rates different or the same? They are the same. They are not different. So, let's review. Do we need to run Levene's f-test for the dependent samples t-test? We just did the independent samples. Obviously not. We do not run Levene's f-test for the dependent samples t-test. Why? Because we assume the variances are going to be the same anyway. Because the dependent samples t-tests are usually on the same people. It's on you twice, right? Your midterm versus your final exam. It's you. The variances are going to be the same, so we assume they're the same. So, what are the assumptions for doing these t-tests? There are 3 assumptions, despite the fact that they got 1, 1, and 1. It should be 1, 2, and 3. First is that these are random samples. Okay, so how do we know that? Because our study design tells us that. Second, that we have a normal distribution. And third, that the variances are more or less the same. How do we know if the cases are random? As I mentioned, based on the study design. How do we know if they're normally distributed? Well, there's a test. That is the Kolmogorov-Smirnov test for normality. And if we can't do that test, then we say that, if there's more than 40 cases, then it's probably normal. Here is the Kolmogorov-Smirnov test output. Again, I don't ask you to compute it. I just ask you to interpret it on the output. In this case, the p-value for the Kolmogorov-Smirnov test is 0.2. Is that low or high? That's high. Why is it high? Because it's higher than 0.05. So, what do we do then? We reject the null. What null? We reject the null hypothesis for the tests of normality, not anything else. There are a bunch of null hypotheses being done here, right? So make sure that your null hypothesis is associated with the right test. The test for normality has a null, and that null is that the data is normally distributed. Did we reject the null? We did not. We retained the null. Therefore, the data is normal. When can we skip the Kolmogorov-Smirnov test? As I mentioned, if there are more than 40 cases per group, we can usually assume it's already normal. And if the 2 groups are more or less the same size. What does more or less the same size mean? Well, one of them isn't more than 1.5 times bigger than the second. What if it's not normal? What do we do if it's not normal? I didn't tell you about that. I'm telling you now. You do a different kind of test. Usually it's something called a Mann-Whitney U-test, which is also called the Wilcoxon-Rank sum test. In this class, we will not be doing that. I may ask you when to do these tests. I'm definitely not teaching you how. So don't worry about learning how to do them, but it might be useful for you to know that they exist. So, the independent samples t-test, as we just said, we need Levene's f-test to determine if the variances are equal. We need to run the Kolmogorov-Smirnov test to determine if they are normal or not. Technically, the independent sample t-test is called the Welch's t-test. I don't ask you about that. Don't worry about it. But maybe you want to know, because why not? It's a good name. Welch's t-test. The dependent t-test, on the other hand, is also called the paired samples t-test. And this one, we always assume that the variances are the same. And we tend not to run the test for normality, or the Kolmogorov-Smirnov test. But we probably should if the sample size is small. And by the way, you may want to know that when Mr. Student, not his real name, first did the t-test, this is the test he did, the dependent samples t-test. Right, let's talk about significance testing. Significance testing is, again, figuring out if your sample is atypical or not. How far along that normal curve is your sample? Is it less or greater than 0.05? So this is how you do it. There are 3 stages. First is you state your null hypothesis. Okay. Then you compute the t-test, or whatever test you're doing, and then you look up in the back of the book to see if you should reject or retain the null. Or you can just compute the p-value via SPSS and look at the p-value and figure out if it's less than 0.05, then we reject the null. If not, then we don't reject the null. Or we can construct a confidence interval. Remember that thing? Remember that confidence interval is the mean plus or minus something, right? So if the interval includes 0, then what? What does that mean? Well, in the t-test, what the confidence interval tells us is the difference between the two samples. And the interval tells us, what the various differences can be or likely to be. So think about it. If I'm trying to decide if the mean midterm mark is different from the mean final mark, and I'm giving you an estimate of the difference between those means, and in the possible range of values 0 is included, that means it's possible that the difference is 0. If the difference is 0, then the two samples are the same because the difference between them is 0. So that's a fast way of looking at significance testing using a confidence interval. And most professionals would prefer this, confidence intervals. But I want you to be comfortable doing all three. So, more things to remember. If you're looking stuff up in the back of the book for the t-tables, you're going to need the degrees of freedom. I hate defining degrees of freedom for you, so I'm not going to bother. Just think about it as a way of measuring sample size. For the one sample t-test, degrees of freedom is n-1. For two samples, it's different depending upon if it's an independent versus dependent test. And these are the summaries, the formulas for it. You're going to have to know your alpha level. Unless I tell you otherwise, it's always 0.05. You're going to have to know whether it's a two-tailed or a one-tailed test. For t-test in this class, it's always going to be two-tailed. So really, you want to focus on this. Get your degrees of freedom straight. And when you look up stuff in the back of the book, you're looking to compare what you computed as your t-value versus what the table says. If your value is bigger than the tables, then you reject the null. Okay? And when I say your value, I mean the absolute value of your number. If it's bigger than the tables, you reject the null. If the table is bigger, then you fail to reject the null. Examples. Here's some examples from the test. In a t-test situation, confidence intervals are constructed around what? Two separate variances. It's going to be B. Okay? How do you know this? Because a t-test is comparing two means, right, to see if they're different. How do we determine if things are different? We subtract them and see if they're 0. So we're looking for the difference between two means. Is the mean mark of this stats class different from the mean mark of the other stats class? That's what a t-test is doing. In this distribution, what's the mode? The mode is the most common value. Blah, 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 15. Well, obviously 15 is going to be the mode. Straightforward. Another example. Which one is a continuous variable? Number of times married. Well, you can't be married 1.5 times, so it's not that. Car crashes past year. You can't have 1.5 crashes. Number of pages in a book. You can't have 4.5 pages. It's got to be B. Age at first sexual experience. 16.1, 16.2. You can subdivide that as much as you like, or if it's in my case 48.7. I'm kidding. It's a joke. Haha. Come on, work with me here. Okay. Last thing to note. Remind you of my rule. I do not answer any questions about exams more than 24 hours or less than 24 hours before the exam. That means that 5 p.m. today, Monday, is the last time that I will accept any questions, emailed or otherwise. So we do this because everyone freaks out hours before. Professor, I understand. And get your shit together. Get your questions now. We had office hours last week and only 4 people came. So, what can I say? This is an exam, not an assignment. That means you're supposed to do it alone. Right? If you don't do it alone, you're cheating. That means emailing and instant messaging and texting people as well. That's cheating. I'm allowing you to Google shit if you want. I'm allowing you to look anything up. It's open book. So you should not need to ask people. If you are concerned about your Wi-Fi reliability, then you can do it on campus. In fact, the classroom will be open to you. You can do it then if you want. And you have from 5 p.m. till midnight to do the entire exam, which shouldn't take you more than half an hour, to be honest. Right? So it's your responsibility to choose if you want to do them all at once, or do one, take a break, however you want to do them. Right? So it's your responsibility to budget your time accordingly. Don't be foolish. Be strategic, people. Okay, that is all, I believe. So good luck to all y'all. And I'll see you next week. Bye-bye.